Today we will discuss about the law of mass action. Law of mass action. This law gives the relationship between molar concentration of reactants and the rate. Gives the relationship between rate of reaction, rate and molar concentration, or you can say the active mass. Molar concentration of reactants. This law was proposed by Goldberg and Wage. Proposed by Goldberg and Wage. Goldberg and Wage. In 1864. So first of all, the statement of this law is at constant temperature, the rate of a chemical reaction is directly proportional to the active mass of reactants. At constant temperature, the rate of a chemical reaction is directly proportional to the active mass of reactants. Active mass. Sometimes it is written molar concentration also, but molar concentration and active mass are not the same thing. We will discuss it later. But here, in case of active mass, we use molar concentration term. So this is the statement. Actually, active mass means all the mass of the reactants are not active. That means all mass are not reacting in the reactions. Some mass are active and others are inactive. Alright, it will be discussed, or we will discuss it later. Active mass. So suppose there is a reaction having reactant A, it forms the product. So according to the definition or the statement, the rate of the reaction will be directly proportional to the active mass or molar concentration of A. So the molar concentration of A can be written as A in square bracket. This is the mathematical expression. Rate of the given reaction is directly proportional to the molar concentration of A. You can simplify it. M plus rate will be equal to molar concentration of A. We know when proportionality symbol is replaced by equal, a constant is multiplied in the right hand side. So here we multiply the constant K. K is a constant and is known as proportionality constant. In this case, it is known as rate constant. So K is here rate constant. So rate is equal to rate constant into the molar concentration of reactant. Suppose there are two reactants, A and B product. Here the rate expression will be, rate of this reaction will be equal to rate constant and the molar concentration of A and B. The molar concentration of A and B. Suppose there are 2 moles of A product. Here this case rate will be K into A and A, or K into A square. So we can write the statement as follows. The rate of a chemical reaction is directly proportional to the product of molar concentration of all the reactants. Okay, if there is one reactant, then you can say the rate of a chemical reaction is directly proportional to the molar concentration of that reactant. But when there are more than one reactants, we can say the rate of a chemical reaction is directly proportional to rate of chemical reaction will be directly proportional to the molar concentration of all the reactant. Molar concentration of directly proportional to the product of molar concentration of all the reactants. If there are 5 reactants, suppose 5A, the rate will be proportional to 5A, a to the power 5. Okay. So the modified statement of law of mass action can be written here is, at constant temperature temperature must be kept constant, otherwise this law is temperature must be kept constant, because when we change temperature, the rate constant, the value of rate constant also changes, and this equation will not hold good. So temperature is kept constant. At constant temperature, the rate of a chemical reaction is proportional to the molar concentration, proportional to the product of molar concentration of all the reactants. We have to add one thing here. With each reactant term, with each reactant term, rest on the power equal to rest on the power equal to the stoichiometric coefficient, the balanced, the coefficient of that species, you can note down also, species in the reaction. So this is the general statement of law of mass action. Suppose A moles of A and B moles of B are reacting and forming the products. So rate will be in this case equal to rate constant and the product of the reactants. Here two products are there, A and B. So the molar concentration of A and molar concentration of B. And each reactant species is raised to the power equal to the coefficient of that species in the reaction. So coefficient of A is A. So here the power will be A and the power will be B. So this is the general statement of law of mass action. Hope you all get it. Now we will discuss the rate law. Rate law. Rate law. Rate law. Suppose A moles of A is reacting with B moles of B and it's forming the product. In general sense, A moles of A are reacting with B moles of B. If it is experimentally found that out of A moles, M moles of A are reactive with N mole of B. Out of A moles, M moles of A are reacting with out of B mole, N moles of B and forming the product. And here M is less than A and N is less than B. So all the molecules of A are not participating in the reactions. Similarly, all the molecules of B also not participating in the chemical reactions. If it is the case, then here the rate law is applicable. According to law of mass action, the rate will be rate is equal to rate constant molar concentration of A to the power A and molar concentration of B to the power B. This is according to law of mass action. But according to rate law, the rate expression will not like this. The rate expression will be rate constant into molar concentration of A and molar concentration of B. But here the power will be, the power of A will be M and B will be N. If all the A moles of A are reacting with B moles of B, then we can replace A in case of M and B in case of B, provided the condition applied when all the molecules of reactants are participating in the reaction. If all the reactants are not participating, then we have to write that value here which are experimentally found. So if out of A molecules, M molecules are participating, then we can write M in place of A and N in place of B. So this is the experimental rate expression. So rate law is obtained from experimental data. Okay, I am taking an example here. The decomposition of N2O5 nitrogen pentoxide to NO2 and O2. Homogeneous state, all are in gaseous phase. Okay, I can balance also 2NO2 and 2O5, 4NO2 and O2. From law of mass action, we can write the rate. So the rate of this equation will be, reaction will be K into N2O5. But the experimental rate is not this. Experimental rate is different. Experimentally, the rate is found to be rate is equal to rate constant into N2O5. From this, we know that out of 2 moles of N2O5, only 1 mole is participating or reactive, and other 1 mole is not participating. So rate law is the experimental data, and law of mass action is not the experimental data, but the statements are same. So the statement of rate law is the rate of a reaction statement the rate of reaction is expressed the rate of reaction is expressed in terms of the reactant, sorry, in terms of the product of molar concentration of reactant, molar concentration of reactant, molar concentration of reactants with each concentration term, with each term raised to the power describing the true dependence, DEPN, true dependence of the rate, on the concentration, this power may or may not be the same as the stoichiometric coefficient. The power may or may not be the same, the stoichiometric coefficient. The powers may or may not be the same, the stoichiometric coefficient, with the stoichiometric coefficient of reactants. So this is the exact definition or exact statement of rate law. So simply, at constant temperature, the rate of a chemical reaction